All right, let's dive into one of the most powerful and honestly, one of the most beautiful ideas in all of mathematics, Taylor's theorem. But we're not going to treat this like a dry textbook formula. Oh no, we're going to look at it as an art form. It's the art of getting incredibly close to an answer, especially when the perfect one seems totally out of reach. So let's get our hands dirty and see how this masterpiece gets built.
It all starts with a question you've probably never even thought to ask. You've done it 1,000 times, right? You punch something into your calculator, like e to the power of 0.5, hit enter, and bam, an answer with a ton of decimal places just appears on the screen. But how? I mean, really, what is actually happening inside that little plastic box? Well, here's the thing. At its heart, your calculator is kinda dumb. It's not magic. It can only do 4 things: add, subtract, multiply, and divide. That's it. There's no special little chip inside that just knows the value of e. So how on earth does it build a number as complex as that, using just those 4 basic tools? And here's the big reveal. It doesn't find the exact value. It gets incredibly, ridiculously close by using one of the most important tools in all of science, approximation. The whole game is about building a simpler model, using only stuff we can do, that acts almost exactly like the complicated thing we're trying to figure out.
Okay, so how do we build that simple model? Well, we're going to start with the simplest guess you could possibly imagine. We're going to call it the tangent line trick. Picture some wild, curvy function. It's all over the place. But if you zoom in, like really, really close on any single point on that curve, what happens? It starts to look like a straight line. That line is called the tangent line. And for any point super close by, the value on that simple straight line is a pretty darn good first guess for the value on the complex curve. This is our first building block, a technique called linear approximation. Now, this idea isn't just pulled out of thin air. It's actually tied to a really deep mathematical rule called the mean value theorem. And don't worry, it sounds way more complicated than it is. All it says is that if you drive 120 miles in 2 hours, your average speed was 60 miles per hour. And for that to be true, you must have been going exactly 60 miles per hour at some single moment in time. It connects the big picture to a single instant, which is exactly what our tangent line does. It uses the instantaneous speed, or slope, at one point to guess where we're headed. So, a straight line is a good start. Not bad for a first try. But, it's straight. It completely misses the bendiness of the curve. We can do better. So, how do we build a better approximation? Simple. We add another layer. And this is the core recipe for a Taylor polynomial. It's brilliant. First, we pin our approximation down at a point we already know, making sure the values match up. Then, we make sure it's pointing in the right direction by matching the slope. That's the first derivative. But then, and this is the key, we also match its curvature, its bendiness, using the second derivative. And the most amazing part? We don't have to stop there. We can keep matching the third, fourth, fifth derivatives, and on, forcing our simple little polynomial to copy the original function almost perfectly. So let's circle back to our old friend e to the x. If we build our first level approximation around the point x equals 0, where we know e to the 0 is just 1, we get a super simple formula, 1 plus x. And what's that? It's just the equation of a line. It's our tangent line, our first guess. But we want to do better, right? We want to capture that curve. So we add the next piece of the puzzle, the one that matches the curvature. For e to the x, this gives us a new term, x squared divided by 2 factorial. And just like that, our approximation isn't a line anymore, it's a parabola. And you can just see it, can't you? It's starting to hug that original curve much more closely than the straight line ever could. And we just keep going. We add another term for the third derivative, then the fourth, and so on. Each new little piece we add makes our polynomial hug that original curve even more tightly and over a wider and wider area. Each term is just simple stuff: multiplication, division, addition. But when you stack them all together, you can build an almost perfect clone of a function you could never calculate directly. Okay, this is all great. We can keep adding terms to get closer and closer. But this leads to a really important question. When do we stop? I mean, who has time for that? How good is good enough? Seriously, think back to the calculator. It has to give you an answer, like, instantly. It can't be sitting there adding terms forever. So how does it know when it's done enough work? How can it be so sure that the number on the screen is correct to the last decimal place it shows you? And this right here is what makes Taylor's theorem so unbelievably powerful. It doesn't just give us the recipe for making the guess, it also gives us a precise formula for the error. It's called the remainder term, and it tells us the exact size of the gap between our simple polynomial and the real thing.
So think of it like this. We have two parts. There's the Taylor polynomial, that's our estimate, the thing we can actually calculate. And then there's the remainder, which is the exact error, the little bit that we're off by. Now here's the kicker. We don't even need to calculate the remainder exactly. The formula lets us figure out the absolute biggest it could possibly be. We can put a hard limit on it so we always know the worst case scenario for our error.
And that is how the calculator does it. Let's say it needs to calculate e to the x, and it needs the error to be smaller than, say, 0.00001. The remainder formula tells it exactly how many terms it needs to add to guarantee that. For this particular problem, turns out the answer is at least 9. So the calculator just runs through 9 terms of the polynomial and calls it a day, totally confident that the answer is perfect for its display.
So as you can see, this isn't just some neat calculator trick. It's a fundamental philosophy for how we understand the world. It is, truly, the art of getting close. And when I say this idea is everywhere, I mean it is everywhere. It's working behind the scenes every time your computer calculates the sine of an angle. It's used in deep number theory to find ridiculously good fractional approximations for numbers like pi. It was even the mathematical engine that was supposed to power some of the very first mechanical computers, like Charles Babbage's incredible difference engine. So, we've seen how we can build a bridge from the simplest arithmetic all the way to the most complex functions we can imagine, getting as close as we could ever need to the true answer. Which kind of leaves us with one final thought to chew on. In a world where we can always get close enough, what does it truly mean to be exactly right?